In this video, we'll look at subspaces. In this problem, we're given the set S. It's a set of vectors x, y, z in R3 such that 2x plus 3y plus 5z equals 0. The problem is if S is a subspace of R3, then we should prove it. If S is not a subspace of R3, then we should give a counterexample. First of all, we should be familiar with the three axioms for a subspace. First of all, the zero vector should be in S. Second of all, if you grab any two vectors in S, their sum should be in the set S. And thirdly, if you grab any vector in S and any real number C, then that scalar multiple of your constant times your vector should be in the set S. Now, if all three statements are true, then S is a subspace. And if at least one statement is false, then S fails to be a subspace. Well, let's try to get a more concrete description of the vectors in S before we start checking the axioms. What I'd like to do is go back to this equation here, this 2x plus 3y plus 5z equals 0, and let's see if we can solve for z. So we'd write 5z is equal to negative 2x minus 3y, and we can divide through by 5. So minus 2/5 x minus 3/5 y is equal to z. Now we can take this expression for z and we can actually plug it back in to the vector x, y, z. And that way we're saying the set S is really the set of vectors that look like this. First two components can be anything, x and y, but the third component is forced to be minus 2/5 x minus 3/5 y. In other words, the third component is forced to be minus 2/5 times the first component and then minus 3/5 times the second component. There's no restriction on the first two components, so we might want to say something like where x and y are any real numbers. So I think we'll find as we're trying to check our axioms that this more concrete description of S is useful. We're more able to understand the form of the vectors in S. So I think I'll put a box around this. And we can start checking our axioms. So let's look at the first statement. We want to know whether the zero vector is in S. Well, if we let x equals 0, y equals 0, let's see what that forces for the third component. Yep, the third component would also be 0 because we'd have minus 2/5 times 0 minus 3/5 times 0. So we can say yes for sure, 0, 0, 0 is in S, and that statement is true. So I've just recopied our revised definition of S from the previous screen, and let's go ahead and check the second statement. So the idea is that we're supposed to start with any two vectors in S. You might say something like let u and v be in S. But in fact, we should probably be a little bit more specific here. When we say that u and v are in S, what we're really saying is that they've got this form here. So it may be a little bit better to say let u be the vector. Well, first component could be anything, second component could be anything, but the third component must be minus 2/5 times the first component minus 3/5 times the second component. To say that the vector has this form means exactly the same thing as saying this vector is in S. So that form is incredibly important here. We'll say let u look like this, and let v, let's say v looks like v1, v2. Again, if we want it to be an S, then we need the third component to be minus 2/5 v1 minus 3/5 v2. So I'm going to say let u and v be in S. Now we need to check whether the vector u plus v has the right form. So u plus v is going to look like u1 plus v1, u2 plus v2, minus 2/5 u1 minus 3/5 u2 plus this expression over here. So minus 2/5 v1 minus 3/5 v2. So in this step, all we've done is just use the definition of vector addition to add the relevant components together. Now what we're trying to do ultimately is to show that u plus v is in S. So we need to show that u plus v has the right form. And we'll be able to do that just by rearranging this third component here. So from this expression here, let's go up to the top over here and we'll just do a little bit of rewriting. We're now thinking of the first component as this object, u1 plus v1. The second component is this thing here, it's the number u2 plus v2. And we want the third component to be minus 2/5 times the first component. So minus 2/5 times u1 plus v1 minus 3/5 times u2 plus v2. So what I've done here is I've really written down what I wanted to get. We just need to check that in going from this step to this step that the algebra or the arithmetic is valid. So yes, we've just rewritten it. We've grouped these two terms together first, and then we've grouped these guys together, and we do in fact get what we want. So now we can say u plus v is in S. We know that because this vector here has the right form. So I've again recopied our revised definition of S, and we'll now look at that third statement and see whether it's true. So what we need to do is grab a vector in S, and as we said in our previous discussion, probably a good idea to be really specific about what that vector looks like. So let's say first components could be anything, we'll call them u1 and u2. But if this vector is going to be in S, then we already know what the third component is going to be. It's going to have to be minus 2/5 u1 minus 3/5 u2. So we'll say let u be in S. And we'll say let C be any real number. Now we're going to take a look at the vector C times u. So scalar multiplication of a vector is defined just by multiplying the scalar through each of the components. So if we do that, we get cu1, cu2, and then c times minus 2/5 u1 minus 3/5 u2. And our goal is to show that this vector here is in S. So in other words, we need to show that this vector has the right form. We need to show that it has this property up here. So with a little bit of algebra, we should be able to show that our vector looks like this. First component is cu1, second component is cu2. What we'd really like to have here is minus 2/5 times the first component. So minus 2/5 times cu1 minus 3/5 times cu2. That's what we want, and we should just check that in moving from this step to that step that the algebra really is valid. Yeah, all we've done is multiplied the c through and just rearranged the order of those factors there. So this was valid algebra here, and we have shown that cu has this form that we want. So therefore, cu is in S. Third statement is true. We've now shown that all three statements are true, so we have in fact shown that S is a subspace of R3.